Okay, thank you for having me. My name is Otani from Kyoto University, and today I am here representing the LignoStella project of Kyoto University. And I truly appreciate this opportunity to be able to join this community. And I hope to learn as many things as I can and take back to the student team. This is my first time giving a presentation about LignoSat in English, so please bear with me. Okay, a brief introduction about myself. My name is Otani, and I'm an undergrad in aerospace engineering at Kyoto University. I'm currently in the final year, and I am graduating next March. I joined LignoSat in May 2024 as a member of the structure team. And as for LignoSat, we are consisted of about 40 active members, and the team is divided into 5 major sub-teams, which are CDH, command and data handling, communications, EPS, electronic power system, and mission and structure. As for what I've worked on in the structure team, so because LignoSat was our university's first attempt at CubeSat projects, we partnered with QTech, and I participated in the first vibration tests for our upcoming satellite at QTech. I also work on our CAD models and structural analysis of the CAD models. And currently, we're running experiments on deployment switches aboard the LignoSat that I'll expand on later on. Okay, next slide. Okay, this is a table of contents. I'll talk about LignoSat first and what we did after LignoSat's launch. We had a few experiments regarding LignoSat's results. And finally, I'm going to talk about successor models of LignoSat. By the way, this is a picture of LignoSat leaving ISS. This is the JSOD module on the upper right corner. And LignoSat is the satellite in the middle. You can see the wooden panel. Okay, next slide. So at LignoSat, Professor Takao Doi leads the LignoStella project, which was launched in 2020 as an attempt to use wood as a new material in space. So Professor Takao Doi, who is a former JAXA astronaut, he was appointed as a visiting professor at Ryukoku University in 2025. So we currently have 2 student groups situated in, one is situated in the original Kyoto University, and the second one in Ryukoku University in Shiga Prefecture. So the current main lab is situated in Shiga. So us Kyoto University students, every time we conduct like experiments, we have to move to the Shiga campus. Okay, and this is the logo for and a picture of the flight model for LignoSat. Okay. So what was the background of using wood in space, first of all? So as all of you know, there's a big increase in satellites up in space. And during atmospheric re-entry, when the satellites re-enter Earth's atmosphere, alumina particles are generated from the aluminum parts and metal parts. And this becomes a potential for extreme weather, ozone layer depletion, and maybe jet engine malfunctions on airplanes. And we thought of this as a major problem. So we're aiming at a sustainable satellite development system. And we chose wood because it burns up completely during re-entry, only producing water and CO2. And we chose Japanese magnolia, and in Japanese, this is called hōnoki. and we selected it through a vacuum exposure test aboard the ISS that was conducted in 2020. Okay. This is the picture. This is a picture of the flight model that was launched in space for LignoSat. And as you can see, there are wooden panels on every 6 face of the CubeSat. And as for the bus system, we used QTech's BIRDS program. And you can see the solar panels and an antenna that's attached to the exterior of the satellite, but the wooden structure inside is connected together without using any metal parts. And we asked a workshop in Shiga that handles like the restoration of national treasures in Kyoto and such to handle precision processing of wood. And because in the GEM payload accommodation handbook, JSOD requires CubeSats to be covered, the exterior to be covered in aluminum frames. We couldn't make the whole satellite wooden, but as you can see in the pictures, there's an aluminum frame covering the sides of the CubeSat. And okay, the 5 major missions for this satellite were: 1, measure strain in wooden panels; 2, measure internal temperature of a wooden satellite; and 3, measure internal geomagnetism; and 4, count SEUs. This is a single event upset; and 5, amateur radio mission. And these are to assess the effect of wood as a new material in space. This is a short video showcasing the deployment of LignoSat from the JSOD module. And you can tell LignoSat, you can maybe tell LignoSat from the color that the wooden panel shows. The LignoSat is in the middle. Okay. And thanks to the JQ program, we were able to launch our first CubeSat in October 2024, and it was deployed from the ISS on December 9, 2024, for the JSOD number 30 program. And it completed its orbit in April 4th, 2025, when it re-entered Earth's atmosphere. And we attempted to receive downlink signals over a total of 184 passes above Kyoto at the Kyoto University ground station, but no signals were received at any point prior to the re-entry. And this is a graph showing the height of LignoSat. Okay. And this is also a video showcasing what the satellite would be like orbiting the Earth. And whenever the satellite passes over Kyoto, we would send a command telling it to downlink towards us to for us to see the data it acquired during Earth's orbit. And yeah, it was going to be like this, but we couldn't see any downlink data as a result. Okay. And so we considered this a failure. So we attempted to analyze the faults using the FTA method, fault tree analysis method. And 2 major faults were found as a result. And one was satellite activation failure, and the second was antenna deployment failure after the satellite activates. We organized the factors into ground station, structural, power supply, and software systems, and examined the likelihood of each factor occurring by cross-referencing them with operational results and ground test data and verification records from prior to the handover to JAXA at Tsukuba. The ground station successfully received signals from the other satellites that were launched in the same JSOD program, the other two satellites. And as for the EPS system, power wiring and critical boards passed the pre-handover checks and end-to-end testing before the handover. So we disregarded these two factors out, and we chose. So yeah, I will talk about the structural factor and the software factor. So we conducted a test. We are conducting a test on the deployment switches. And as for the software, we upgraded the interpic communication system, and I will expand on these two on later slides. And yeah, I will discuss the countermeasures we took and how we upgraded or are aiming to upgrade the satellite accordingly. Okay, about deployment switches. So on your left, you will see an engineering model of LignoSat, and on the -z base of LignoSat, there are three deployment switches, and in the upper right corner, there is a spring plunger, and it is supposed to push LignoSat from other satellites during deployment from JSOD. But deployment switches are placed inside the structure, and it pokes out from the aluminum frame. And we, as for the experiments, we connected LED lights to each switch. So yeah, the goal for this experiment was that we thought deformation of the wooden panel or the aluminum frame could have caused the deployment switches to maybe stick inside the aluminum frame or fail to open upon release from JSOD, and it maybe prevented the satellite to power up. So the goal of the experiment is to verify whether the wooden structure as well as the aluminum frame caused the deployment switches to fail under space environments and different atmospheric environments. So the picture you see on your right is a rig that we developed, and it is placed inside a vacuum chamber. And using this rig, we monitored the displacement of each switch upon release. And okay, the rig moves a plate along the z-axis like this to press and release the three deployment switches. And we monitor the displacement of the switches and the how and when and where the LED lights illuminated. And this the rig, there's a panel with on the rig that pushes all three deployment switches at the same time. Okay, here are the results that were acquired from the experiment. On your left is the one we did in the condition of 12 days under atmospheric pressure, and the right one is 11 days under vacuum, 0.0034 pascals. In both conditions, the switch actuation positions remained stable. And for the next steps, we are thinking of solar panel. Going back to the next slide, we didn't attach solar panels in the antenna for this experiment. So in future experiments, we're trying to attach solar panels and recreate what LignoSat might have gone through aboard ISS and in vacuum. And we finally were considering thermal vacuum tests at QTech in the future. Okay, next up is flight software updates. And on your left, there's a diagram of the antenna deployment system. And the problems were that the reset pick could freeze, which could prevent the COM picks to power up. And the second flaw was that the interpic communication failures may have blocked the antenna's release. So in order to fix this, the reset pick timer now checks the main pick communication to reset the watchdog if the watchdog is stuck. And we configured the main pick to trigger antenna deployment independently. In order to reduce risk of blocking the antenna from releasing. Okay, now on to successor models. On your left is a picture, an image of LignoSat 1R. We call this LignoSat 1R. And two obvious modifications have been done. And one is that the dipole antenna has a 45-degree angle, and this is to prevent the magnetic interference between the antenna and the aluminum frame. And we're also planning to add a LED indicator for the power system so that we could see if the satellite has turned on after a deployment, and we could see from the ISS. Which allows us to, if future problems were to occur on LignoSat 1R, we can isolate the startup issues from communication system issues aboard LignoSat 1R. Okay. This is okay. We haven't named this satellite yet, but we are planning to name it LignoSat 2. And this is a 2U sized CubeSat, and LignoSat 1R's success could expand the potential of using wooden satellites in space. For this satellite, we leveraged the radio wave transparency of wood and we placed patch antennas inside the satellite. And also attitude control is achieved using permanent magnets and hysteresis dampers. And these new systems are planned to be installed in the additional 1U section. Okay. Okay, that'll be all for my presentation. Thank you for your attention. I will try to answer any questions according to my knowledge, but I might not be able to answer some of them. So if so, please contact me at this email address, and I'll check back with the team and prepare answers. Anyways, thank you all for my presentation.